with the geometries.
Okay. Yeah. Well, so I'm going to talk about a long-term research effort that is from a relatively large collaboration scattered all over the world. It's with Brent. It's kind of part two of Brent's talk, together with Joanne Simon Soler, Yang Hui He, James Gray, Vishnu Jayala, and Brent, of course. So the outline of my talk is basically to review the large volume scenario as it has been kind of explained in the paper by Michele, Joe, and Fernando. Then I'm going to show how we kind of reformulated the explanation of the large volume scenario in terms of divisor volumes, of divisor four-cycle volumes, in terms of the Kähler parameters. And finally, I'm going to explain how this, in the end, helped us to find a reasonably efficient implementation that allowed us to scan a relatively, a large set of toric Calabi-Yau hypersurfaces. And in the end, I'm going to show how this will be generalized subsequently in order to broaden this scan. So the original large volume scenario claim, as I mentioned in this paper here from 2008, can be essentially summarized to this statement. You have a Calabi-Yau manifold, set of divisors, and the tau i's are the volumes of those divisors. So those are, to emphasize, is four-cycle volumes. And the large volume scenario claim is then essentially that the large volume limit is defined that you take a number of the four cycles to go large, so that the overall volume goes large, while a number of the four-cycle divisors remain small. So the idea is you have a couple of smaller holes in your manifold and kind of large cycles which more or less determine the overall volume. Furthermore, the Kähler potential and the superpotential have to take a particularly form. In the end, the idea is to have a moduli stabilization of that, but here this is not really too relevant for us. The moduli stabilization aspect is of course the physical motivation for that, but we are essentially more looking at the moment at the geometrical implications of that. So first, what I have to say, the statement as it's made in said paper, of course implies that the divisor basis that is given can be directly split up in large and small cycle divisors, which is of course in terms of writing a paper a very simple assumption, but computationally, if you want to do a scan of generic manifolds, it couldn't be more evil. So this is actually what Brent yesterday in his talk referred to as manifests with cheese. There were a couple of notions that we developed kind of during the research project, which are probably not official or anywhere else mentioned. So manifests with cheese is if you can really split up the divisor basis. So the central idea which kind of brought us forward, we originally started by directly diagonalizing the intersection form, and that was completely impossible in terms of computational effort. So one of the central insights was basically to rewrite the large volume limit, so basically the original statement here, in terms of the Kähler parameters in order to get in the end, mostly coordinate independent statement. This essentially rests on the Poincaré duality, which maps four cycles to two cycles, so in the end basically the taus to the t's. And then basically instead of sending the taus to infinity, we're going to send certain directions in the Kähler parameter space to infinity, which, if you know at the kind of expression of the taus in terms of the t's, is an equivalent statement. So the idea is to split up a Kähler parameter vector, a generic Kähler parameter vector, in kind of the same number of, correspondingly to the taus in a number of large directions and a number of small directions, and then analyze what the corresponding statements are for those vectors. So the large volume claims of the volume going to infinity, or rather the large cycles going to infinity, corresponds to then sending the corresponding parameters of the large directions to infinity. So what does small and large then actually mean in terms of those Kähler parameters? Now, if you take the definition of the taus, as mentioned before, and simply plug in this split up vector here, you get this expression, and you basically just have to do a power counting for the lambdas. So as you know by the coloring, everything blue is large, everything red is small, just to ease up a little bit looking at this stuff. What you see is in the first two terms, you have large parameters. So in the first two terms, if those are non-vanishing, then by sending a certain linear combination of the lambdas to infinity corresponds to the fact that this will be a large volume, a large direction, so a large Four cycle. And well, you can simply break this down here by saying large Four cycles are characterized by either this term or that term, of course ranging over all the A's and B's here, being non-zero, whereas small cycles are characterized by those terms vanishing. And in fact, if you look at it, L ranging over all the B's and here S ranging over all the small B's, that gives you a generic vector. So the small cycle condition can actually be summarized in this fashion. Actually, something I've mentioned, the small kappas are basically just a restriction of the intersection form to one of the divisors. So it's basically just take the first index and single it out to that particular divisor. It's probably important because it appears a couple of times. The central benefit is now this is a linear equation, which is a huge simplification later on. The second aspect is that if you read said paper carefully, there is the important property of a blow-up mode condition, which relates to the inverse scalar metric. Particularly, it relates the diagonal of the inverse scalar metric for the small cycles to the overall volume and the volume of this small cycle. Now, then you use this general expansion of the Calabi-Yau manifolds inverse scalar metric and plug this all together. What you basically get is this has to be equal to this statement here, which if you think a second about it and use the previously derived statement, means that the right-hand side, which obviously only depends on the small cycle volumes due to the vanishing, requires this side to only depend also on the small cycles, which then in particularly implies that you get this statement out of it. I'm just trying to explain very quickly how we arrive at our final equation system. Furthermore, since there is a duality between the taus and the t's, the complete collection of the large directions and the small directions has to be a basis itself, and in particularly non-trivial, well, it has to be a basis. So essentially just require the determinant of the arising matrix to be non-vanishing. If you think a little bit about it, by identifying small cycles and just caring about the small cycles, due to the fact that there is an actual duality behind it, this immediately implies that you take care of the large cycles. This is a little bit quick at this step and, like I said, requires some thinking, but it's another simplification because you can throw out another set of equations. And which is very important, now that you are talking in terms of the t's, of the Kähler parameters, you have to take care of the Kähler cone. The Kähler cone is essentially, can be characterized as a number of inequalities, so you're shaping a cone, which can be represented by a matrix which then combines with the components of one of the ti vectors. Here is once again the general idea behind the large and small cycle distinction explained. So in the end, with respect to a convenient basis, like I said, I have to overemphasize the convenient basis here. We arrive at this set of equations in order to identify a Swiss cheese manifold. So what you basically is, you take this set of equations and solve basically for all the parameters that are in there. It looks worse than it is, but it still isn't very good at this stage. The important point, like I said, of rewriting all this in terms of the Kähler parameters is that you lose most of the dependency of the coordinates. So there are, of course, here the alphas, so you still have the convenient basis, but for example, the contractions between the Kähler parameter basis and the divisor basis, that all kind of goes away. So next step is how to go to an arbitrary basis now. Well, there is no real magic in it. You simply take a generic base change matrix and apply it to the proper places, which is fortunately only in those two cases here. Now the Kähler cone condition from this statement here would unfortunately then involve an inverse of the A matrix, which would be absolutely terrible if you do a scan, because you have a generic matrix that you are going to solve for as well. The inverse thereof which looks extremely awkward. And
are the first two conditions independent or
Sorry?
together?
The
first two conditions are they independent, and once you satisfy the first one, the second one is automatically satisfied?
But if I set TL and TS to 0, then that's a campus.
Yeah.
So no,
There are definitely, I'm going to come to it. This equation is definitely not irrelevant. It is reasonably irrelevant in the sense like if you have a high H11, this condition is almost always satisfied. In fact, when we did our scans only for H11 equals 2, this actually became relevant, which we are going to use in a scan later on. So, oh God. So the Kähler-Kohn condition following this approach would get immensely screwed up due to the inverse. Therefore, we simply normalize the Kähler-Kohn, considering that we now start with an arbitrary basis. We restrict ourselves to manifolds which have a simplicial Kähler-Kohn. That basically means that the number of faces of the Kähler-Kohn is equal to H11. So basically the matrix that defines the Kähler-Kohn becomes an invertible matrix. So we kind of transform the intersection form, the divisor basis, and also the Kähler-Kohn, so that we get a nice normalized Kähler-Kohn, which immensely simplifies our Kähler-Kohn condition then. And this would kind of be our final set of equations in order to identify a Swiss cheese manifold. Like I said, we now have to solve for all the variables that are in there, and it's still quite a demanding task. So the number of free variables in this unchanged basis is really, it grows immensely. So if you do it in practice, you will find that only for H1 equals 2, it's actually directly doable if you just plug it into Mathematica. If you go to any higher H11, this becomes way too slow. However, there are quite a number of redundancies. If you think about it, the generic Kähler-Kohn parameter was split up with linear factors. And on the other hand, we have here now vectors which have no restriction on their length. So there is still a lot of redundancy where you can actually turn inequalities to equalities by fixing numbers here. Requires some thinking, and anyway, you can fix those. And equalities can be much simpler solved computationally. Like I said, this condition here is almost always trivially satisfied. So the idea is simply ignore it at first and simply test it later on. Like I said, only for H1 equals 2 we actually found that it becomes really important. Nevertheless, Mathematica is still too slow, but fortunately there is a package called Singular which does essentially Gröbner basis computations, which those are solutions to polynomial systems, just to keep it short. And one can also fix quite a number of the free components in those vectors that we are solving for, and also in the base change matrix, simply by thinking a little bit about the high level of redundancy that is in there. And in fact, this is also what took a considerable portion of our time to get the right combination of all those tricks properly together. So in the end, what you have is fix the number of large and small cycles to test for. So far we've only been doing scans where the number of large cycles is 1, so small is H11 minus 1. Then compute the Gröbner basis for this reduced set. Actually compute the dimension of the Gröbner basis, which is a separate step in Singular, much faster than computing the actual Gröbner basis. For this subset of the equations, if this dimension is non-negative, then we perform a primary decomposition. Gröbner basis is usually in terms of complex solutions where we actually need real solutions, in fact only the integer solutions. We add the Kähler-Kohn conditions to each component of this primary decomposition and then solve it in Mathematica. Each component is usually much simpler than the entire system. And in the end we simply test the k-1 alpha alpha condition, as we've dubbed it. And well, if all this is passed, we call it a Swiss cheese. And so in the end, like Brent already mentioned on the summary slide, we've tested H11 smaller and equal than 4 for one large cycle. But as you see here, this is all completely general for higher numbers of large cycles, which is from a phenomenological point of view quite interesting. I mean, phenomenological viable models usually have at least 2 large cycles and have then H11 equals 5. This is generalizable. Just today we managed by a couple of further fixings to go as high as H11 equals 8, at least for some simple manifolds. So this should all go much further. And yeah, but what we're also going to do is looking at strong versus weak Swiss cheese, which basically means can you diagonalize the volume form as it is usually done for Swiss cheese manifolds, or does it keep kind of off-diagonal terms, in particular involving the small cycles? And one statement that I can also give here, the complete intersection Calabi-Yau manifolds for H1 smaller or equal than 4 are all not Swiss cheese, which already rules out kind of a significant set. So there is a lot to discover still in the Swiss cheese landscape.
Okay, questions?
How restrictive is the condition for simply circular cone? So experimentally, how can we?
Oh god, hopefully I don't screw up the numbers. Do you still remember the numbers? I think for H1 equals 4, for example, I mean, you start with 1,196 or 7 polytopes, which then gives you around 5,500 triangulations, and 3,600 out of those roughly have simplicial Kähler cones. So there you lose roughly 1/3. In H1 equals 3, it was about 1/6 if I remember correctly. So we had 280? Yeah, I don't remember.
Yeah, or 40%.
Yeah, 10% maybe. So you're probably going to lose more as H1 grows. In principle, I mean, I have to emphasize, this is not really a big problem of our test. The problem is if you really keep the full set of equations here. Like I said, you have an A-1 in there, and you are solving for the A matrix. For H1 equals 5, the general inverse of an A matrix, yeah. And if you try to solve for it, this is really going. This is a catastrophe in terms of computational efficiency. This was basically the main reason why we restricted to that. Maybe there may be a smarter reason to come up.
There is another question over there.
Hi. I just have a slightly off-topic question. Have you thought about like mirror Swiss cheese Calabi-Yau, where the complex structure free potential takes this form? Because you can also realize large volume scenario in type 2A if you have a mirror Swiss cheese Calabi-Yau with complex structure, large complex structure modulator. I mean.
Not yet.
That would be easier because like when you think like these old papers and geometries, sometimes they were calculating things on the complex structure side and they were finding that easier. I don't know if it's easier.
My first thought would be, I mean, our kind of difficulty level grows with H11, and since we're starting with lower H11s and you switch those if you go to the mirror manifold, I would assume that H11 would explode quite a lot. So I'm not sure if
but you're not calculating the same thing. You're calculating a little different.
Any other question? Yes, Timo.
Sorry.
Just person.
Yeah.
So how generic would you say are Swiss cheese manifolds? In the set you said no.
Very
Well,
generic, very
for H1, so for H11 equals 4 in the toric space, we had 360?
Out of?
360 out of 3,600 simplicial ones, out of 5,400 toric hypersurfaces. So
Pretty generic.
about 10%, about 10% Swiss cheese out of the set that we can scan. That would be the statement at H11 equals 4, and the assumption is probably that it's going down a little bit. I don't know. We can't say yet.
But this would be the assumption of one large cycle.
Okay.
Yeah, with one large cycle. I should
And if you
emphasize.
relax that,
I think we should move on to the next talk, otherwise
All right.
we can discuss it.
Okay.
Thank you. Let's finish.